Hello everyone, and welcome to today's presentation. I'm excited to talk with you about nitrification in activated sludge systems. The title of our talk is Nitrification in Activated Sludge Systems, and we'll explore how this essential process helps us treat wastewater effectively. Over the next few minutes, we'll cover the key aspects of this biological process, why it's so important, and how it impacts modern wastewater treatment. Let's get started. Let's take a closer look at the nitrogen cycle in wastewater treatment. At the start, we have what we call organic nitrogen input. This includes proteins, amino acids, and urea that come from domestic and industrial wastewater sources. These compounds enter the treatment system and begin the process of nitrogen transformation. Next is ammonification, where heterotrophic bacteria play a key role. They decompose these organic nitrogen compounds and convert them into ammonia, or NH₃ N. This step is crucial because it makes nitrogen more accessible for subsequent treatment processes. Then we move into nitrification. Here, autotrophic nitrifying bacteria step in. They oxidize the ammonia into nitrite and then further convert nitrite into nitrate, all under aerobic or oxygen-rich conditions. This transformation is vital because it prepares nitrogen for removal in the later stages. After nitrification, we have denitrification. Facultative bacteria take over in anoxic zones, areas without oxygen, and reduce nitrate into nitrogen gas, which is released harmlessly into the atmosphere. This step completes the biological nitrogen removal process. Overall, the nitrogen cycle in wastewater treatment is like a carefully balanced ecosystem. Multiple bacterial populations work in sequence to transform potentially harmful nitrogen compounds into harmless nitrogen gas. Understanding how these processes connect is essential for operators to optimize treatment and meet stricter discharge standards. Modern activated sludge systems are designed to handle both carbon removal and nitrogen transformations at the same time. This requires sophisticated process control to ensure each microbial community has the right conditions to do its job effectively. And remember, the success of nitrification directly impacts how well downstream denitrification can proceed. When nitrification is efficient, overall nitrogen removal is maximized, which is critical for protecting our environment and meeting regulatory requirements. Let's dive into the fundamentals of nitrification, which is essentially a two-step biochemical process that transforms ammonia into nitrite and then into nitrate. This process is quite intricate, involving specific bacteria and environmental conditions, but it's one of nature's most efficient methods for detoxifying ammonia. First, in the initial step, ammonia is oxidized to nitrite. This is catalyzed by ammonia-oxidizing bacteria, like Nitrosomonas species. The chemical reaction involves ammonia reacting with oxygen to produce nitrite, water, and hydrogen ions. It's important to note that this step requires about 3.43 milligrams of oxygen per milligram of ammonia nitrogen oxidized. Also, this reaction produces acidity, which consumes alkalinity, so pH management becomes important here. Then, in the second step, nitrite is further oxidized to nitrate by nitrite-oxidizing bacteria, such as Nitrobacter and Nitrospira. This conversion also needs oxygen, about 1.14 milligrams per milligram of nitrite nitrogen. When you combine both steps, the total oxygen demand comes to roughly 4.57 milligrams per milligram of ammonia nitrogen nitrified. Now, regarding energy, both steps generate energy for the bacteria, but the energy yield is relatively modest compared to other microbial processes. Interestingly, ammonia-oxidizing bacteria tend to gain more energy per mole of substrate than nitrite-oxidizing bacteria, which often makes them more dominant and results in higher growth rates. Understanding these details is crucial for designing and operating treatment systems effectively. The oxygen consumption impacts aeration requirements, and the alkalinity consumption means we need to monitor pH closely and sometimes add chemicals to maintain stability. By grasping these fundamental concepts, we can better predict system behavior and optimize performance under different load conditions. Let's take a closer look at some key nitrifying bacteria, Nitrosomonas and Nitrobacter. First, focusing on Nitrosomonas species, these are the primary ammonia-oxidizing bacteria in activated sludge systems. You'll often find species like Nitrosomonas europaea, which have a rod-shaped morphology. They possess an enzyme called ammonia monooxygenase, or AMO, which is crucial because it kickstarts the oxidation of ammonia. In terms of optimal conditions, Nitrosomonas thrive around 25 to 30 degrees Celsius and prefer a pH range of 7.5 to 8.5. They have a generation time of about 8 to 12 hours, which means they grow relatively quickly, and their yield coefficient is between 0.04 and 0.1 grams of volatile suspended solids per gram of ammonia nitrogen. Now, turning to Nitrobacter species, such as Nitrobacter winogradski, these bacteria are responsible for completing the nitrification process by oxidizing nitrite. They use the enzyme nitrite oxidorreductase. Compared to Nitrosomonas, Nitrobacter grow more slowly and produce lower yields. They prefer slightly warmer temperatures around 28 to 35 degrees Celsius and a pH range of 7 to 8.5. Their generation time is longer, about 12 to 24 hours, and their yield coefficient ranges from 0.02 to 0.07 grams of VSS per gram of nitrite nitrogen. Recently, researchers have identified Nitrospira as an increasingly important nitrite-oxidizing bacteria, especially in wastewater treatment systems. Interestingly, Nitrospira often outcompetes Nitrobacter at lower nitrite concentrations because they have a higher affinity for nitrite. They tend to grow more slowly, but are better at surviving in low substrate environments. They typically have spiral or curved cell shapes and are dominant when nitrite levels are low. Understanding these microbial communities is vital because the ecology of nitrification involves complex interactions. These bacteria compete for oxygen and space, and their populations are influenced by predation from protozoa and environmental stressors. All of this affects how stable and effective our nitrification process can be. Now, if we compare growth kinetics, ammonia-oxidizing bacteria, or AOB, generally grow faster and reach higher specific growth rates than the nitrite-oxidizing bacteria, or NOB. This difference can sometimes cause nitrite to accumulate, especially during startup or under stress conditions. NOB tend to grow more slowly and require longer solids retention times to establish stable populations, which is an important consideration in process control. Finally, regarding environmental sensitivities, nitrifying bacteria are quite sensitive to changes. They are more vulnerable to temperature fluctuations, pH shifts, and toxic compounds than heterotrophic bacteria. This means that careful process control is essential, especially to avoid shock loads that could upset this delicate microbial balance and compromise the nitrification process. Now, let's take a closer look at the environmental factors that affect nitrification rates. First and foremost, temperature plays a critical role. It's actually the most significant environmental factor influencing how well nitrifying bacteria perform. The optimal temperature range for maximum activity is between 25 and 30 degrees Celsius. Within this range, bacteria are most efficient at converting ammonia. However, if temperatures drop below 15 degrees Celsius, nitrification efficiency can decline sharply, sometimes severely hampering the process. This is where the Q10 coefficient comes into play, which typically ranges from 2 to 3 for ammonia-oxidizing bacteria, meaning the rate roughly doubles or triples with every 10-degree increase in temperature. During winter, operations face particular challenges. Seasonal solids retention time adjustments are often necessary to maintain process stability, and the lower temperatures can slow down nitrification, requiring operators to be more vigilant. Moving on, pH and alkalinity are also vital. Nitrification consumes significant alkalinity, about 7.14 milligrams of CaCO3 per milligram of ammonia oxidized, and produces acidity. If pH drops below 6.5, nitrification can become inhibited. That's why maintaining pH within the optimal range of 7.5 to 8.5 is so important, often by adding buffering chemicals like lime or caustic soda. Keep in mind, free ammonia becomes toxic above pH 9. So controlling pH is essential not just for efficiency, but also for preventing toxicity. Now, let's talk about dissolved oxygen, or DO, which is absolutely necessary for nitrification. A minimum concentration of about 1 to 2 milligrams per liter is needed to avoid oxygen limitation. Higher DO levels actually improve process stability and help handle peak load conditions. The oxygen transfer efficiency in the system also impacts energy costs, so optimizing aeration is a key part of efficient plant operation. Interestingly, in some cases, simultaneous nitrification and denitrification can occur, which adds another layer of complexity. Next, we have inhibitory compounds. Certain industrial chemicals and heavy metals like copper, zinc, and nickel can inhibit nitrification at very low concentrations, much lower than those affecting heterotrophic bacteria. Organic solvents, quaternary ammonium compounds, phenolic compounds, cyanide, and thiocyanate can also pose challenges. Being aware of these inhibitors is crucial for maintaining a healthy nitrification process. Moving on to nutrient requirements, nitrifying bacteria need essential nutrients, but in different ratios compared to heterotrophs. For example, the optimal phosphorus to nitrogen ratio is about 100 to 5, and they also need trace metals like iron, copper, molybdenum, as well as inorganic carbon sources, magnesium, and potassium for growth. Finally, the physical environment within the aeration basin significantly impacts nitrifier performance. Factors such as mixing intensity, floc structure, hydraulic retention time, and loading rate variations all influence how well nitrification proceeds. Light exposure can also affect microbial activity. Managing these physical conditions requires diligent monitoring and responsive control strategies. Modern treatment plants incorporate advanced process control systems to keep conditions optimal while minimizing energy and chemical use. Understanding how all these factors interact helps us predict potential upset conditions and maintain a stable, efficient nitrification process. Let's now look at the key design parameters for achieving optimal nitrification performance. First, the minimum solids retention time, or SRT, should be between 8 and 15 days. This means the solids in the system need to stay long enough to maintain a stable population of nitrifying bacteria under the given design conditions. If the SRT is too short, the bacteria can't establish themselves effectively. Next, the minimum dissolved oxygen, or DO, concentration should be around 2 mg/L. Maintaining this level ensures that nitrification occurs efficiently without oxygen becoming a limiting factor. Adequate oxygen supply is crucial for the bacteria to carry out their nitrification process. Moving on, the food-to-microorganism ratio, or FM ratio, should be about 0.05 kg BOD per kg MLSS per day. This ratio is optimized to support nitrification while still allowing for effective carbon removal. Balancing this helps ensure the bacteria have enough food without becoming overwhelmed. For pH, the optimal target range is around 7.5. Keeping the pH within this range maximizes nitrification rates and helps prevent ammonia toxicity, which can hinder bacteria activity. Now, let's discuss some critical design considerations. The aeration system must be designed to meet the high oxygen demand of nitrification, typically using fine bubble diffusers for efficient oxygen transfer. These diffusers often have alpha factors between 0.4 and 0.8, indicating their efficiency. Standard aeration efficiency ranges from 1.8 to 2.4 kg of oxygen per kilowatt-hour. When designing the aeration system, it's also important to calculate the peak oxygen demand, incorporate turndown capabilities to handle variable loads, and ensure maintenance access. Basin configuration is another key factor. Reactor geometry impacts mixing, oxygen distribution, and hydraulic flow. Generally, plug flow reactors tend to outperform completely mixed systems for nitrification because they promote better conditions for bacteria growth. Process control infrastructure is essential for stable operation. This includes online ammonia and nitrate analyzers, dew and pH control systems, and temperature compensation algorithms. Monitoring alkalinity and implementing chemical feeds, along with variable frequency drives for blowers, help maintain optimal conditions. The nitrification process occurs in 3 phases. First, during startup, we seed the system with nitrifying bacteria and gradually increase load over 4 to 8 weeks. Then, during acclimation, bacteria populations develop and performance is fine-tuned over 2 to 4 weeks. Finally, in stable operation, we rely on consistent performance and established monitoring protocols. Remember, these parameters should also account for seasonal changes, peak loads, and future expansion plans. Safety factors, typically between 1.5 and 2, are applied to critical parameters like SRT and aeration capacity to ensure reliability. In conclusion, successful nitrification design is a careful integration of biological needs, mechanical systems, and control strategies, working together to deliver reliable, efficient performance under various operating conditions. Let's now take a closer look at process control strategies and monitoring techniques. First, advanced control approaches are essential for maintaining optimal nitrification performance. Feedback control is the traditional method, where we base adjustments on effluent NH₃ N measurements, tweaking dew and pH to keep concentrations within target ranges. Then there's feed-forward control, which is more proactive. It uses influent characteristics and loading patterns to anticipate changes and adjust operating parameters before issues arise. For even more sophistication, model predictive control employs advanced algorithms and process models to optimize multiple objectives simultaneously, such as effluent quality and energy efficiency. Effective process control hinges on continuous monitoring of key performance indicators. Modern plants utilize both online sensors and laboratory tests to keep tabs on critical parameters. For example, measuring ammonia nitrogen levels in influent and effluent helps assess removal efficiency. Monitoring nitrite nitrogen prevents toxic buildup, while nitrate nitrogen levels indicate how complete the nitrification process is. Total inorganic nitrogen gives an overall picture of nitrogen transformation, and alkalinity consumption reflects nitrification activity and chemical needs. In addition, secondary indicators like the specific oxygen uptake rate, nitrification rate potential tests, microscopic examination of floc structure, and settling characteristics provide deeper insights into system health. Control responses are often automated in modern plants, allowing for real-time adjustments of aeration, sludge flow rates, chemical dosing, and even process configurations. When issues occur, troubleshooting involves diagnosing symptoms, say, high effluent NH₃ N or nitrite accumulation, and identifying likely causes through diagnostic tests like SRT calculations or microscopic analysis. Corrective actions might include reducing wasting, increasing aeration, or adjusting pH levels. Successful process control integrates real-time monitoring, predictive modeling, and operator expertise. Increasingly, plants are adopting artificial intelligence and machine learning techniques to further optimize performance, reduce energy consumption, and minimize chemical use. Ultimately, the goal is to create a resilient, efficient system that responds intelligently to changing conditions. Let's dive into some of the common operational challenges and troubleshooting strategies we encounter in activated sludge systems. First, establishing stable nitrifying populations is often one of the most challenging parts of system commissioning. Cold weather startups, in particular, can be quite tough and may require anywhere from 8 to 12 weeks to reach full nitrification capacity. To manage this, we focus on factors like seed sludge procurement and ensuring high-quality inoculum, maintaining temperature control during startup, and implementing gradual loading increase protocols. Monitoring how the populations develop over time is crucial, and having backup aeration and heating systems can make a significant difference if conditions become adverse. Next, let's talk about shock loading and toxic upsets. Industrial discharges or accidental spills can seriously impact our nitrifying bacteria, which are more sensitive than heterotrophic bacteria to toxic compounds and sudden environmental changes. Specific toxins like heavy metals, copper, zinc, nickel, organic solvents, or abrupt pH shocks from discharges can cause problems. High-strength waste slugs can also create stress. Recovery from such events usually takes about 2 to 6 weeks, so early detection and rapid response are essential. Moving on to seasonal performance variations, temperature fluctuations throughout the year significantly influence nitrification rates. During winter, lower temperatures slow down the biological kinetics, so we need to adjust our SRT, consider supplemental heating, and sometimes make process configuration changes. Ensuring permit compliance during cold periods requires proactive management strategies to maintain consistent performance. Now, let's discuss diagnostic approaches and solutions. Systematic monitoring is your best friend here. Regular checks, daily on parameters like dissolved oxygen, pH, temperature, and visual inspections, help you catch early signs of trouble. Weekly lab tests for ammonia, nitrites, nitrates, and alkalinity give deeper insights, while monthly detailed analyses, including sour testing and microscopic examinations, help assess population health. Quarterly, a comprehensive evaluation of the microbial community and kinetic parameters ensures your system remains optimized. In case of an upset, having emergency response procedures in place is critical. Rapid response minimizes downtime and prevents permit violations. Recovery strategies should be patient and gradual. They include reducing organic loading, maintaining optimal environmental conditions, considering supplemental seeding, and monitoring the reestablishment of populations. Slowly returning to full loading helps prevent secondary problems. When troubleshooting, start with problem identification. Recognize symptoms early through routine monitoring. Conduct root cause analysis by reviewing process data, lab results, and on-site observations. Implement corrective actions based on your findings and closely monitor how the system responds. Confirm resolution through continued checks, and then develop prevention strategies to avoid future issues. Remember, successful troubleshooting depends on understanding the complex interactions within biological, chemical, and physical processes. Experienced operators develop intuition about system behavior, allowing them to anticipate problems and implement preventive measures before they escalate. That proactive approach is key to maintaining a resilient and efficient treatment process. Let's now turn our attention to energy considerations and how we can optimize costs in wastewater treatment plants. As we analyze energy consumption, we find that aeration blowers and pumping systems are typically the biggest contributors, especially in nitrifying activated sludge systems. In fact, aeration can account for between 55% and 70% of the total energy used in the plant. This is largely because nitrification requires a high oxygen demand, around 4.57 milligrams of oxygen per milligram of ammonia nitrogen, which significantly raises energy costs compared to systems focused only on carbon removal. So, how can we address this? One key strategy is aeration optimization. Advanced control systems, such as demand-based aeration and precise dissolved oxygen control, can cut energy use by 15 to 30% without sacrificing treatment performance. Think about installing variable frequency drives, profiling oxygen levels in different zones, or using ammonia-based aeration control. These are all ways to fine-tune the process and save energy. High-efficiency blowers and diffuser maintenance also play a crucial role here. Next, process configuration offers another avenue for savings. By making strategic modifications, like implementing step-feed operation to balance loads, or integrating biological nutrient removal techniques, we can improve efficiency and reduce energy needs while maintaining or even enhancing treatment quality. Membrane bioreactors and hybrid systems, like moving bed biofilm reactors, are also promising options for better performance and lower energy footprints. Equipment efficiency is another critical factor. Modern technologies, such as turbo blowers versus traditional positive displacement blowers, high-efficiency motors, and smart control valves, provide long-term operational savings. Additionally, recovering heat from blower cooling systems, or employing energy-efficient mixing equipment can further optimize energy use. Now, let's talk about economic optimization strategies. A comprehensive life cycle cost analysis considers not just the initial capital investments, but also ongoing operational expenses, maintenance, and equipment replacements over the system's lifespan. This helps us make smarter decisions that balance upfront costs with long-term savings. Performance-based optimization involves fine-tuning operations to meet treatment goals efficiently while controlling costs. This requires sophisticated control strategies that can balance multiple parameters simultaneously, ensuring we meet regulatory standards without unnecessary expenditure. Emerging technologies also offer exciting opportunities for energy recovery. Waste heat from blowers can be repurposed, biogas can be used for heating, and solar heating systems can reduce reliance on external energy sources. Energy storage and peak shaving strategies are also gaining traction to manage demand and reduce costs during high-usage periods. In terms of potential savings, advanced control and process optimization can lead to around 25% energy reduction. Predictive maintenance and equipment upgrades can save approximately 40% on maintenance costs. Additionally, process controls and alkalinity management can cut chemical costs by about 15%. Ultimately, successful cost optimization is about finding the right balance, achieving effective treatment, complying with regulations, maintaining equipment reliability, and ensuring sustainability. Modern plants are increasingly adopting integrated approaches that consider energy efficiency, process resilience, and environmental impact all together. Looking ahead, the future trends and innovations in nitrification technology are truly exciting. From now until 2024 to 2026, we're seeing emerging technologies like AI-driven process control, advanced sensor networks, and energy optimization algorithms. These advancements are already beginning to enhance how we monitor and manage wastewater treatment processes, making them more efficient and smarter than ever before. Moving into the near term, roughly from 2027 to 2030, we can expect to see bioaugmentation technologies, which involve introducing beneficial microorganisms to improve process stability. There will also be novel reactor designs and integrated resource recovery systems, turning treatment plants into sources of valuable nutrients and energy rather than just consumers. Looking further ahead, beyond 2030, the innovations become even more revolutionary. Synthetic biology applications will allow us to engineer microorganisms tailored specifically for wastewater treatment, enhancing performance and reducing energy needs. Quantum sensing technologies will provide ultra-precise real-time monitoring, enabling us to control biological processes at the molecular level. And eventually, we'll see fully autonomous treatment plants that operate with minimal human oversight. Artificial intelligence and machine learning are already transforming nitrification control, predicting equipment failures before they happen, forecasting influent loads, optimizing energy use in real time, and detecting process anomalies early. Future developments like digital twin systems, automated decision support, and self-learning algorithms will further streamline operations and improve reliability. On the biological front, breakthrough approaches such as the anammox process, partial nitritation optimization, and bioelectrochemical systems are promising to overcome traditional limitations, reduce energy consumption, and stabilize processes. Synthetic biology takes this even further by designing microorganisms that not only enhance treatment, but also produce valuable byproducts, opening new economic opportunities. Next-generation sensor networks, including quantum sensors and optical technologies, will give us unprecedented insight into biological processes at the molecular level, enabling precision control like never before. Resource recovery will become a core part of future systems, capturing nutrients, energy, and materials from wastewater, turning treatment plants into energy producers and resource recyclers. As climate change accelerates, resilience becomes critical. Future nitrification systems will need to adapt to extreme weather, temperature fluctuations, and changing influent characteristics, ensuring reliable operation under all conditions. We're also moving toward integrating treatment with the circular economy, recovering nutrients for agriculture, energy for communities, and water for reuse, making wastewater treatment a key driver of sustainability. Finally, achieving net-zero energy operations and carbon neutrality will be a real focus, leveraging renewable energy, improved efficiencies, and carbon capture technologies. In essence, the future of nitrification technology is a convergence of biological innovation, digital intelligence, and sustainable engineering. These advances will not only improve wastewater treatment, but transform it into a vital component of our circular economy and environmental stewardship, always with the goal of protecting public health and our planet.